Good morning, everybody, again, and welcome to Physics 3, basically. We are still finishing ideas with chapter 37. I must tell you upfront that we're a little bit behind schedule in terms of where we need to be. I'm just looking at the syllabus. And I made some changes, and I sent a message concerning Lab 5 again, okay? As a matter of fact, Lab 6 will be due before Lab 5. So Lab 6 will be due on the 19th of this month. And Lab 5 has been pushed to after the spring break because of the fact that it has an essential component in it. Half of the lab deals with nuclear physics, okay? And because we really did not cover that topic yet, I know part of it we did, which is the mass energy equivalence, which is basically E equal to mc squared for the case when the particle is not moving. However, it's more than that. It actually goes into the nuclear binding, basically, of different atoms, if you wish. Yeah, the atoms. And it includes actually corrective terms, not just that one. It includes the Coulomb force, basically, and how much that would account for the binding, for the nuclear reaction, if it's possible or not. So basically, I have reactants and you have products, and you're supposed to calculate the binding energy for the products and that of the reactants. And you're supposed to find the difference between the two to determine if this nuclear reaction is endothermic or exothermic. Basically, does it require energy to work, or can it happen on its own, like radioactivity, for example? It turns out in the lab itself, actually, it goes a step beyond and that introduces a correction due to Coulomb's interaction. It's not just the bonding basically between different nuclei, like proton-proton or proton-neutron or neutron-neutron, but it actually goes a step beyond, and that is actually includes the interaction between the charges, the positive charges from one nucleus interacting with another nucleus. So there will be a repulsion in there. Because of that, and we didn't really cover that yet in this class, and we will not cover it really until chapter 42. So we're still way behind in terms of where we need to be in terms of that. So I postponed the lab until at least to get some tracks, some things going on, so that we have a full understanding of that part. The first part with the lab 5 deals really with the stuff that we've been covering, namely the length contraction, the time dilation, simultaneity and the lack of, and what else does it deal with? That is, I mean, the first part really all you have is, first of all, some calculations involving gamma and beta, and the second part deals with the with how can you fit. I'm going to take this example in here. This is a station, and this is a ship. Okay. How can you fit this ship inside this station? It doesn't make sense. I mean, at least from the rest frame where we're sitting, it doesn't fit. It won't go in. But if the ship is traveling super fast, its length is contracted, its length is shrunk. And it should fit in the sense that the front of the ship will go in, and then the back of the ship actually will go before this one will reach the end. So in other words, it's going to fit because the length is contracted. So this is from the vantage point of the station that is sitting and seeing the ship coming and going in. So this is the ship will fit in. But from the vantage point of the ship, it's actually the station that is moving toward it. So the length of the station actually shrinks. So you need to find a way so that, again, this will fit. And again, because of the lack of simultaneity. Okay, that is going to fit. So this is the first part of the lab, really, that deals with the length contraction and simultaneity of two events. And then the second one deals with the time dilation. Basically, it has two twins. I think their names is Leah, I forgot the other one. One of them travels to a faraway star and then comes back with almost the speed of light. For that traveling twin, basically the time is shrunk. The time is not going as fast as the person who's sitting in here and observing the twin brother traveling or the twin sister traveling with with almost the speed of light. So in that case, you calculate the time from the vantage point of the twin at rest, from the vantage point of the twin and moving, and then you determine the difference in time. And they promise each other in the lab that they would send every year a message. And actually, there is an animation in here in the lab. If you look at it, it tells you, it shows you as the twin brothers. Let me show you the animation since I'm talking about it. This is the lab basically as the twin brother starts traveling. After 1 year, the one who's traveling in here sends a message, and the other one sends after his 1 year or her 1 year. And the orange dots are from the traveling twin, and the white dots are from the twin at rest. And this animation basically illustrates the point that at the end, the twin at rest is almost 10 years old, whereas the other one is about half of the age of the other one. So basically, they will age differently because one of them is traveling with the speed of light and the other one is not. Obviously, you're supposed to do this calculations and find all the numbers and all of that. But this is really the hiccup in here, okay? You're supposed to have this Excel file, and you've opened this Excel file, which I'm going to open in a, let me get it to open separately outside to show you that this Excel file has wealth of data. Let me open it, and then I will share with you the Excel file quickly. And you need Excel for this one. Did it open at all? Okay, it did. So let me show you. Share. No, not this Excel file. The nuclear data. This Excel file has a lot of data, okay? And as you can see, as I am scrolling, I am at the row 167 right now. So it has a lot of data in it. And it's a nightmare trying to find something in here because, for example, for cobalt, this is all of this different types of isotopes of cobalt that you have in here for nickel and so on and so forth. So it has basically a lot of data, and you cannot really do it manually. This is something that has to be with search and find or do something, okay? Let me tell you what I'm talking about, okay? Just to show you where this thing ends, okay? We're out of 1,500 lines. Okay, it's a lot of scrolling, okay? And we are at basically at the bottom, about 3,000 lines, okay? 3,200 lines in here. No, I did not. Actually, this is the data that we have from a, it was shared with the college, so we have that, okay? Nobody had to type this one manually. You know, this stuff is exported to CSV file. Later on, you're going to have it, you enter it basically. Okay, let's say, for example, I'm here and I'm looking for uranium, okay? I do, or let's say, for example, for iron. Control F, and then I find iron. And symbol is Fe. And if I do find next, it's going to take me to where I need to be. Obviously, when you're doing this lab, I have to look for the specific isotope that they're talking about. B is usually the atomic number, and the number of ions, Z and A. And let me show you another trick also on how to handle this one. Let's enable editing. And come in here and make sure that this line, what is the split line in here? View. Where is the freeze? Freeze, okay. Freeze panes. Freeze the top row, that's all. That's all we need. So again, if I'm looking at iron, Control F. The reason why it's a good idea to freeze lines is because then you can know what these numbers are, okay? So this is iron. This is the Z number, which is the number of protons in it. This is the number of neutrons. This is the sum of the two. This is the atomic mass, AMU, okay? Actually, this is the AMU. It's both in mass, which is 45.0145, and this number you will need. That's why you're actually searching for this thing in here. And then it's in mega electron volts, the binding energy also, all of these values in here, but usually the main number that you're looking for is this number, okay, to do calculations. Because you can multiply that number by 1.6605 times 10 to the negative 27 kilogram, the mass of one AMU, atomic mass unit. And then you multiply that by c squared, and you already have the energy in joules. But again, you divide by 1.6 times 10 to the negative 12 and negative 19 to get it in electron volts, or 10 to the negative 13 to get it in mega electron volts. Okay, and at the end, you're going to do calculations because everything is supposed to be in MEV. So again, this is a long thing to do, okay? And also you really need to have some understanding, especially when you have to make corrections due to Coulomb force. That's why this lab, I'm kind of delaying it a little bit until we get some, so we cover some grounds in the topic. Then we're going to have it, then we should be able to do it and understand every single step of it. Make sense to you guys?
Yes.
Yeah, so I just have a question for you. So because these labs are being delayed now, are we just going to be doing like a really long lecture today? Is that the plan? Or
okay, we have two things to do today. Okay, we have some problems that I promised we do, and then we also have to get started with chapter 38.
okay.
Sounds good. I will take a break in between, and depending on how tired everybody feels and how I feel tired, then we probably have to call it a day. But then I may have to share with you some resources related to the lab, and hopefully you guys will get at least started with the first part, which should not be hard. Okay. Granted that lab 6 is going to be due before lab 5 because of the fact that we should have enough materials for the photoelectric effect to have the lab, okay, for it. So we will have lab due, and probably we'll have 2 labs before that lab is finally basically done. I think for the future times, I'm going to split it into 2 labs. I'm going to have 2 labs, one for pure relativity, and the second one is for nuclear physics, taking the value from relativity, because the value for the energy in this case is actually all of it is coming from relativity, that square root of stuff that has MC squared and things like that. Okay, so it's like we have to split this lab. Anyway, what is chapter 37 now? Problems. We did already problem 38, didn't we? Yes.
Yeah, you did problem 38. Yeah.
Okay, very good. Before I do that problem, let me say something that has to do with the lab also, okay? Do something that has to do with the lab and with the problems that you're going to be dealing with within this chapter. And that has to do with the kinetic energy that we found last time. Okay, every time you're dealing with relativity and you're asked about kinetic energy or something that has to do with it, you're supposed to use the formula that we derived last time, which is the kinetic energy. So guys, remember, is gamma minus 1 times mc squared. So this is the kinetic energy. And the total energy is just gamma mc squared, or the square root of mc squared plus p squared c squared. That's the same thing, okay? So this stuff is from lecture. Here is the deal though. I made a claim last time, and which is really has to be, we have to hold ourselves accountable to, and that is we're building a new theory, which is the special theory of relativity. The reason why it's special, it's because, as I said last time, it's dealing with this metric. Oh, let me write it in general, okay? I don't want this negative sign in here. Plus, we called it dx squared, but we could potentially add dy squared and dz squared in general. And these are two, both of them, we're taking them 0 anyway, because we're just considering the case where the things are moving with respect to the x-axis. It's hard to include this one in here. Even visualizing it is hard. I mean, trying to draw a 4-dimensional space in to the flat surface is hard. I mean, if you try to draw a 3-dimensional space, you always have this representation that you guys are doing with the assumption that this somehow is a 90-degree angle, and this is a 90-degree angle, and this is a 90-degree angle, but you're doing it on a flat screen, okay? Which is kind of, we're extending our imagination to see that there is an incoming arrow coming off of it. Now imagine this and try to draw a 4-dimensional line where there is some sort of a vector in here that is perpendicular to this one, and perpendicular to this one, and perpendicular to, I don't know how I'm going to even draw it, this one. So it's perpendicular to all of them in the same time. So it's going to be even, so this is basically the picture of a four-dimensional picture. So it's going to be hard. Anyway, so this is basically what we did last time. This is the metric. What is it? That we're dealing with. And because of that, it's called the flat, basically, because there is no deformation in it. That's what we're dealing with the special theory. The point being in here is this has to reproduce all of your classical things. Everything has to do the attitude, the incline, the I don't know, waves on a string, and whatever you did, friction, for example, of a mass spring system where you have a mass, all of these results must be reproduced by this thing, because those are things that we know are true. So this thing has to also produce these things. Here is a value of the kinetic energy that I was talking about. Every time you're asked to calculate it, this is technically what you're supposed to do. Even in the classical sense, even if you have a very slowly moving object with V that is extremely small compared to C. This is technically the value that you're supposed to do. If you know the mass of the object, you can find its gamma, depending on how fast it's moving. This is the kinetic energy. But does this look anywhere near 1/2 of mv squared? Are they the same? This is for the classical case, when V is extremely small compared to C. Doesn't have C in it at all. Do you guys see that?
Yes.
And this one has a C squared, but gamma is embedded in, V is embedded in that gamma. You see that? So this appears to be that. So here is the deal. We need to get some sort of a sense of scale of this one, because that's really the first question of the lab. You're supposed to get a lot of these, and you're supposed to compare them and see when is it going to be relevant to use expressions like this one, and when is it relevant to use expressions like that, okay? I know we're saying V is extremely less than C, but how small? That's the question, really. So let me go back into the correct value of the kinetic energy that we found last time, which is gamma minus 1 times mc squared, and write that gamma as, remember, it's 1 minus v squared over c squared to the power negative 1/2. That's exactly what the gamma is. And v over c, I'm going to call this one a tiny number, which I'm going to call epsilon. The reason why I'm calling it epsilon is because I know in classical physics this is true. That this number is so small. I mean, v over c is small, let alone v squared over c squared. Does this make sense?
What does that E stand for?
I'm sorry?
What does that E stand for? Or is it an E in between the V squared over epsilon? What does it stand for?
It's just this ratio of v squared. I mean, I know I usually call beta being v over c, but I'm calling actually v squared over c squared as a tiny number, epsilon.
Okay, thank you.
Okay. The reason why I write it epsilon, every time we're dealing with something tiny, we call it epsilon. Okay. That's really the convention. Okay. So gamma is equal to 1 minus epsilon to the negative 1/2. Okay. I'm not writing beta, because if I do write beta, I'll have to write beta squared in here. And I really don't want to take derivative with respect to beta, where I have to take the negative 2 beta times d beta and all of that thing. So I'm just going to deal with this term in here. So this is a function of epsilon, which is v squared over c squared, by the way. Yes?
Yes.
Yes.
Okay, according to somebody, either McLaurin or Taylor or both of them or somebody in there, they said that the approximation of this function is gamma, because epsilon is very small compared to 1, so I can evaluate it at 0 plus the derivative of gamma with respect to epsilon evaluated at epsilon equal to 0 times epsilon plus 1 over n factorial. Oh, I need the second term. Okay, in the expansion, which is 1 over 2 times the second derivative of gamma with respect to epsilon times epsilon squared. This evaluated at epsilon equals to 0, plus now this thing plus the nth factorial, the nth derivative of the function f with respect to epsilon, evaluated at epsilon equals to 0, times epsilon to the power n, plus some other stuff. This doesn't end. This is a, what did you call this expansion? Is it Taylor or a Taylor-Maclaurin, or is it Maclaurin, or whatever you guys call it?
Yeah.
Is this okay? This is Calc 2 anyway. Is this Calc 2 stuff?
I don't
Yes.
think so.
It's toward the end of Calc 2, from what I understand. No?
I think so.
I don't remember it.
I know, right?
This is the stuff that you did in it should be. I mean, this is, I mean, there is an easy explanation for it in physics. Actually, the whole idea was so that when you take the subsequent derivatives of this function, you're going to reproduce all of these experiments, basically. Somebody mentioned something. What happened, Natasha? You guys don't see what I wrote in here?
Oh no, I'm saying that like we forget everything that we learned after the final.
So you erase everything out of it. Okay, well, this we needed, okay? At least to this term in here, up to the second term, okay? Well, gamma of 0 is clearly equal to 1, because it's 1 minus 0 to the power -1/2, so which is 1, okay? Gamma, derivative of gamma with respect to epsilon, you can clearly see the wisdom of using not beta, but epsilon, because all I have to do is drop that -1/2 from the power, then take the derivative of inside, which is -1, then drop the power by another factor, which is brings me to -3/2. Evaluate this expression at epsilon equals to 0. Well, the negative cancels the negative. This one is 1, so it's just 1/2. Okay. Now I need the second derivative with respect to gamma, because I'm getting to the second term in here. And that is, if I can find where the mouse went. Okay, the second derivative now of gamma with respect to epsilon. Remember, I have a -1/2 times negative, that's a +1/2 already in the expression. Times the derivative of this term, I drop a -3/2 already, and I take the derivative of the inside, that's -1, and times the whole power to drop by another 1, which brings me to -5/2. Okay, evaluate this expression at gamma at epsilon equals to 0. The negative and the negative become positive. 3/2 times 1/2, that's 3/4, times 1. Because again, when epsilon equals to 0, that's 1. Okay, so that's all I need after the second term. I'm going to ignore any other term because epsilon is very tiny anyway. Okay?
Professor, what's your upper limit for the derivative or integral or derivative?
Well, we don't do upper, just evaluate the derivative at that point.
Oh, okay.
Yeah, we evaluate the function. Let me write it in your the way that you probably are familiar with it. Okay, you write it as f of x equals to f of 0 plus the derivative of f with respect to x evaluated at x equals to 0 times x plus the derivative of f with respect to times 1/2, by the way, 1/2 factorial, which is 2, evaluated at x equals to 0 times x squared plus the general term, which is 1/n factorial times the nth derivative with respect to x. So this is not a power, this is the derivative, okay? Evaluated at x equals to 0 again times x to the power n plus terms that go forever and ever. It never ends really. It's a sum to infinity. This is how you wrote it probably, okay? But because we are dealing with the function gamma in here as a function of this tiny number in here, which is v²/c², I just changed the symbols a little bit. Does this now ring a bell? Hopefully this does.
Yes.
Yes. Okay. So sometimes when the symbols change a little bit, things start to become strange. Anyway, so the first term is 1. That's gamma of 0. The second term is, this one is actually 1/2, because when we evaluated d gamma over the epsilon, we found that it's 1/2. When we evaluated the second derivative with respect to epsilon and evaluated the epsilon, that's 3/4. But don't forget that extra 1/2 in here. And everything else after that, I'm going to ignore. So gamma then becomes gamma of epsilon, or gamma of v squared of c squared, which we're going to submit. So gamma of 0, I'm sorry, let me write it exactly what it is, which is 1. So this is 1 plus the leading term is 1/2. That's coming from the derivative, by the way. It's this derivative times epsilon plus its positive term contribution. All of the contributions are going to be positive. 3/4 times that 1/2 from the Taylor itself. So plus 3/8 times epsilon squared plus terms that I'm going to ignore of the order of epsilon cubed. So anything below that is 0. That's basically how we write it down. Now let me go back into the expression as we wrote it. Gamma as a function of v. So this becomes 1 plus 1/2 of v squared over c squared plus 3/8 of v to the power 4 over c to the power 4 plus terms that are negligible in the order of v to the power 6 over c to the power 6. So in other words, when v is so small, I'm going to ignore, compared to c, by the way, then I'm going to ignore these terms in this approximation. Let me go back into the kinetic energy. Remember, the kinetic energy looked like this, gamma minus 1 times mc squared. So all I have to do is subtract 1 from this expression, which cancels that 1. So this expression would look like, 1 is canceled, by the way. 1 from here and 1 from here are gone. So all I'm left with is this corrections. In other words, I cannot just take the leading term, because if I just take the leading term, then in this case, the kinetic energy is 0. Because if I ignore this term, I will get a 0 kinetic energy. So I need to at least get the first leading term, which is 1/2 times v squared over c squared, plus, now, if I'm being a little bit more ambitious, I can take the second term, which is 3/8 of v squared to the power, d to the power 4, I'm sorry, c to the power 4, plus stuff that I'm neglecting, the whole thing times mc squared. Well, the first term, c squared and c squared cancel. So I'm left with 1/2 of mv squared plus now this stuff in here, which is 3/8 of mv to the power 4 over c squared plus stuff that I'm neglecting. Here is the other 1/2 of mv squared. Here is your classical value of the kinetic energy. This is what you used all along. But when v is slightly bigger, when v is big, then you need to include this correction. So this is the first correction to the kinetic energy when in comparison. So this is a classical kinetic energy. This is the relativistic kinetic energy. The difference between the two, between the k, the real value, and the ke in the classical approximation is at least this leading term, 3/8 of mv to the power 4 over c to the power 2. And this is a very tiny number. Because again, v squared, v to the power 4 over c to the power 4 times mc squared, this is a small number. This is what you need to do to make corrections. So if I neglect this term, the two terms become identical. So if this term is truly 0, the kinetic energy classical value and inner relativity are the same. Remember how gamma really behaves. Let me share with you the screen. If I can find it. Show more screens. This is how gamma is. For the most part, it's in here. Okay? It's very close from 1. So this is the function gamma, if you guys remember, which is 1 over square root of 1 minus beta squared. I'm using back beta because then I can actually graph it with the velocity itself, not velocity squared. Okay? The reason why I did it earlier just for the Taylor expansion, but now I have to really draw it with the function beta. Let me go to the next slide in here, because what I did in here, I took 100% just to convert this ratio to 100% and evaluated the gamma at 2/3 the speed of light, meaning beta is equal to 0.677. So in this case, when it's 67% the speed of light, minus the old classical value, which is 1 times 1/2 of, this is the value of gamma, of course. This is the first leading term in the Taylor series, which is 1 plus 1/2 of v squared over c squared, which is gamma, which is beta squared now, divided by the actual value of gamma, I get about 9% error, less than 10%. So if you're asked in the lab to find how much error, and if you put, for example, the value of 50% the speed of light in here, versus, and this one also becomes the 50% the speed of light, half the speed of light, and this becomes half the speed of light. So if you do the calculation, the error is of the order of 2.5%, because I'm multiplying the whole thing by 100 to get the error in percent. So if you're comparing numbers for the lab, and if you get an error more than 3%, that means you have to include the relativistic corrections. Any error less than 3%, like in this case, ignore relativistic correction. So even if you're going 50% the speed of light, you may ignore it if you're happy with 3% error. Does this make sense?
Yes.
Okay. So when you're doing the lab and you're looking at the first question and it's asking you about different values of the velocity, I'm referring to the lab now. They give you a table with different values of the velocity. Let me find where the lab is. Okay, this is the values. Let me move it to the other screen because I have hard time sometimes working with this screen. Okay, so let me share now. Share the lab. This is just to help you get started with this lab, because a lot of things you can do on your own. Let me show you what I'm talking about, okay? In this table in here, they give you the speed of 29 meters per second. You can find beta by dividing this number by 300,000 kilometers per second, or 300 million meters per second. 3 times 10 to the power 8. Obviously, you can find the gamma in here, which is 1 over the square root of 1 minus beta squared. And is this an error that is within 3% or not? Okay. Obviously, it's going to be small, 330 meters per second. You're still dealing with that divided by, again, 300 million meters per second, and you can find the value of gamma. It's only when you reach about 50% the speed of light, okay? The big M in here stands for mega meters. That means 10 to the power 6. The K in here stands for kilo, like kilometer in here in this case, kilometers, which is 10 to the power 3. So that's, so 290 megameters, that's 290 times 10 to the power 6 meters per second. So in here, your 300 million meters per second, it's still, now you're almost close to the speed of light. So this should be significant. 60 million should be probably, I don't know. You guys continue with this calculation. Does everybody understand that this table is easy?
Yes.
Okay, anybody else also other than Maddie?
Yes.
I hope so, yes.
Okay, so this is part that you can do when you get started in your lab. So this is part of the discussion that I'm trying to say in here. Anytime you find error more than 3%, then you say, wait a minute. Maybe I should take into account the relativistic corrections, okay? That's basically what you can say. So this part, I wanted to extend it with that discussion here. And now let's continue with the problems. Sounds good? And let me write a new line in here and let me share the screen again. Share. Okay, so we have an understanding of what that is, and you guys clearly see 1/2 of mv squared really is there, okay? Classical mechanics is there, okay? Problem 44. By the way, in the discussion for this week, which is, I think, 2 weeks ago, there are some old videos that have problems also that are discussed in there. You're supposed to go through those problems also. You're accountable for them when comes exam time, okay? Problem 44, and that is page 1249. So with this is the page, okay? It says that you have a sigma plus particle. By the way, you can always refer to the same table from chapter 44, which is the page now, 1,490 something or 49 or something. 1,496, I think. Yes, 1,496. And it's table 44.3. If you are really curious about these particles in here, so the K plus is also a meson. Okay, it's made up of two quarks, and it's an up quark and an anti-strange quark. Okay, so it's all of the mesons are made up of two quarks. All of the hadrons, the baryons, basically are made up of three quarks. Okay, so that's also in the same table. So if you're curious about it, you can just look it up in there. But the key thing in here is its lifetime tau, which is usually, we use the letter tau for it, is 80.2 picosecond, and pico is 10 to the negative 12. Okay, so this is its lifetime, 8.2 times 10 to the power negative 12 seconds. Okay, extremely short lifetime. The physicists measure that the mean lifetime is to be 403 picoseconds. So in the lab, the physicist measures to be 403 picoseconds. Okay. As the particle moves in his lab, the rest mass of the particle is 2.12 times 10 to the negative 27 kilograms. So it's slightly more massive than actually the proton. So although it's made up of two quarks, it has more mass than the proton. So the mass is 2.12 times 10 to the negative 27 kilogram, but it's a short-lived meson. Okay. How fast is the particle moving? Again, we can find gamma. We know that in the lab, the time is dilated by the factor of gamma. So tau over gamma. This is the scaling factor. Tau over gamma. Tau times gamma. Gamma tau. I always, and that's really the source of the mistake that we got last time. It's gamma tau, okay? Because gamma is more than 1. It's 1 over the square root of 1 minus beta. So in other words, this value is 1 over square root of 1 minus beta squared. Okay, and 1 over the square root is more than 1. I'm getting a warning in here about my internet being kind of iffy. So if you guys experience any problems, please don't leave. We're going to come back and continue this one. So how fast the particle is moving? We have everything in here. We have this one is 403 PS. And this one is, what is it? 80.2 PS. Cancel the PS with the PS. We really don't need them. Divided by 1 minus beta squared. And from here, you should be able to, actually, we could have found gamma from this expression. Gamma would be just T over tau. And T is 403 divided by 80.2. So from here, we use another expression that we found last time, which is square root of 1 minus 1 over gamma squared. Okay, or beta equals to the square root of 1 minus, in this case, tau over T squared. You guys understand where I'm getting all of this stuff from?
Yes.
Okay, so all I have to do now is find what beta is. Once I find beta, which is V in terms of C, really. Okay, so this is V over C. So we should be able to say that the velocity of these particles are square root of 1 minus tau over T squared. Tau is 80.2, the T is 403, so this is roughly about 1/5, okay, squared. So you can do the math in here. So this is square root of 1 over 5 squared which is what? 24 to the square root of 24 over 25 times c. That's a very large velocity, isn't it? It's almost the speed of light. Obviously, you're supposed to do the calculations. Finish this. Okay, I'm just throwing in a number. It's not exactly 1/5, okay? Because 5 times 2 is 0 times 1, 5 times it's 10. It's going to be slightly less than that, okay? But you're supposed to do it. Make sense?
Yes.
Okay, so we can find how fast it's moving. What is its rest kinetic, its rest kinetic, and total energies in the lab frame? Rest energy is simply mc squared.
Did you do part B?
Did I skip part B? Okay. But part B, how far does it travel as measured in the lab frame? Okay, now that's easy. Since we found how that's velocity, this is how he measures the velocity of the particle. Okay. And he knows its time, how long it's going to live. It's going to live 403 picoseconds. So the distance traveled in his lab is going to be VT. He measured its velocity, which is this quantity. He knows how long it's going to live. So for him, it's going to be c times the square root of 1 minus tau over t squared times t. That's the velocity times time. Or if you really want to write it in a different fashion, d is equal to c times the square root of t squared minus tau squared. We just throw in that in there. Make sense?
Yes.
Yes.
Okay. All he did was, because remember, this is, we're doing a special theory of relativity and there is no acceleration. So everything is in uniform motion. Since we found v, and we know how long it's going to live, so the maximum distance traveled is this number. So let's throw in here and see if it makes sense, okay? How long is the normal lab? Is it like a million miles, or is it like 10 kilometers, or is it like normal lab in life? How big labs are? So this is 403 squared minus 80.2 squared times 10 to the negative 12 squared, and you take it out. So it's going to be times 10 to the negative 12. So 10 to the negative 12 and 10 to the power 8. So it's going to be, what is it? 10 to the negative 4. So the whole thing is in meters, okay? So I'm left with 403 squared minus 80.2 squared. What is that number? Anybody? Or should I get the calculator also? I want to really see. I don't want the it lives 10 kilometers like we did for the mu one, because a normal lab has to be of a normal size. It should not be more than probably 100 meters. 100 meters is a big lab. I mean, 20 meters. Okay, that's a big lab. Okay, so it should be within.
I'm getting 0.118.
I also
Point?
got that.
118. Yes.
Okay, so that's okay. That means it's divided by multiply by 100 divided by multiply by 100. Well, I'm saying in here. So 11.8 centimeters. So that's fine. Okay. If I found it to be a kilometer, then I will have to tell you there's or 118 meters. That's a very long lab. Okay. So you have to be critical of your work. I mean, so the person who put the lab, maybe he throw in some numbers in there for gamma that is so ridiculous that the particle will go straight through the window of that lab and go to the next door window where people are sitting and having lunch. You don't want that, okay? You're going to ruin their lunch. In other words, the person who puts the problems like this one has to be careful with stuff like this, especially if they are juggling the numbers. And this is more of a realistic value in here. What are its kind of rest energy? And so the rest energy is easy. It's mc squared. And mc squared in this case, m is given 2.12 times 10 to the negative 12. So the rest energy, so I'm going to call it E naught, is going to be 2.12 times 10 to the negative 27 times c squared, which is 3 times 10 to the power 8 squared. Okay, 8 squared, which is 16, subtracted from negative 27, that's negative 11. Okay, and then you're left with 2.12 times 9 times 10 to the negative 12, negative 11, I'm sorry. It's a good idea to convert, try to wait to mega electron volts, because that's the unit that we're going to be using. Probably if they don't tell you explicitly, that's a good idea to use it anyway for this case in here. So omega is 10 to the negative 10 to the power 6, 1.6 times 10 to the negative 19, and plus 6, that's negative 13. So cancel that with this, so it's going to be positive 2 in the numerator. Okay, so technically the answer should be 2.12 times 9 divided by 1.6 mega electron volts times 100, because of that 10 to the power 2. Make sense?
Yes.
Okay, so this is the rest energy. And the kinetic energy then, Ke, is gamma minus 1. I already have that extra dash in there. I have no idea why I do that. Gamma minus 1, it's because of this pen, I guess, times mc squared. Remember, you just find E naught. All you have to do is multiply by gamma minus 1. And gamma minus 1, if you guys remember, you already found gamma. Gamma is a ratio of 4/3, 403 divided by, so that's gamma actually. So this should be 403 over 80.2 minus 1 times the value that you find from there. And this is in MeV also. Okay. And the total energies. Well, the total energies, one way of doing it is Ke plus E naught. That's going to give you the value. So E is gamma times mc squared, and that is going to be E naught plus this Ke. So once you find these two numbers, you just add them up. Okay. So that's part C. Part D, what are its rest energies? Oh, I'm sorry. Oh yeah, that's correct. Everything for C, because we're doing it from the lab reference frame, from the particles frame. It's not moving. If you're sitting on the, if you're riding the particle in this case, there is no velocity. You're sitting, you're finding it. So again, E naught is going to be the same value. Ke is going to be 0, and E is going to be just E naught. Okay, because the lab is the one that is moving. As far as it's concerned, it does have a kinetic energy. Make sense?
Yes.
Okay, so that's 44. And then problem 51. 51 is kind of easy. I think it's in the discussion if you guys have had the chance to go through it from week 5, from the week before the exam, I guess. And it talks about the Cherenkov radiation. If you have had a chance to go to a nuclear lab, when I was in the Midwest, we used to go to the University of Rolla, where they have a nice nuclear lab there for nuclear engineering students, where they go through the lab, and you can see when they turn on the nuclear reactor, you can see the Cherenkov radiation. Basically, it's a bluish light. And the Cherenkov radiation, what it is in the tank where they have the when they submerge all of those rods. The beta particles, namely the electrons, as they come out of the rods, they come super fast, and their kinetic energy, or their velocities, are greater than the speed of light inside the water, and they produce that bluish color, which is the Cherenkov radiation. Okay, they don't allow you to take your cameras with you. They confiscate the cameras before your phones before you go in. Otherwise, you could take pictures, and it's really a nice thing to look at. So what it is, basically, in this problem, they give you the index of refraction for the glass, which is 1.52. If we're going to do this one in water, is going to be a different index of refraction. So the speed of light in a medium with an index of refraction n is c over n. So in this case, it's going to be 3 times 10 to the power 8 meter per second divided by 1.52. This is the speed of light in glass.
What problem is this?
Oh, I'm sorry, this is problem 51 on the same page. Okay. So so you have the speed of light. Now, there is nothing to prevent the electrons from moving faster than the speed. The boundary in gamma is not the speed of light inside a medium. It's the speed of light in vacuum. So this is the particles. I mean, this is the speed of light. Okay, so I'm going to put the letter light in here. So we cannot replace this value by the speed of light in that medium. This doesn't work. It works in vacuum. So in this case, the particles can be still moving with speed faster than the speed of light. So the gamma can really be, so this is that of the electrons, they can be moving faster than the speed of light. They're inside the speed of light that goes through the glass in this case. So if we use this expression, they ask you, what is the minimum kinetic energy in electron volts that an electron must have while traveling inside the slab of crown glass? So in this case, basically what you do, you have the kinetic energy for these electrons, which is gamma minus 1, must be mc squared. This energy has to be greater than a certain minimum. And that minimum, when the electrons are at least traveling with the speed, which is less than the speed of light in vacuum. Because the speed of light in vacuum divided by 1, this is divided by a number greater than 1. So in this case, the beta, let's assume that these electrons are moving with this speed. So in this case, beta should be the ratio of this speed with which the electrons are moving, namely c over n, divided by c, cancel the c from both sides. This is the minimum speed that the electrons need to be moving with, or the relative speed with respect to light, the speed of light in vacuum, with which they need to be moving with to exceed the speed that is the limit on that material. But they still can move with the speed. Now it's still less than 1, because this number is 1 over 1.52. Okay. Now if I plug in this value in here for gamma, namely I can find gamma first, which is 1 over the square root of 1 minus this number, which is 1 over 1.52 squared. So I have the value of gamma. All I have to do is sub it into the value in there, and I found the kinetic energy. So basically, the kinetic energy for these electrons need to be equal to this number, 1 over the square root of 1 minus 1 over n squared, minus 1 times the mass of the electron times c squared. Let me set up the numbers for you guys, and hopefully you guys finish it. So the kinetic energy, this is the minimum kinetic energy. They can travel faster. And that's how the Cherenkov radiation happens, actually, which is going to be 1 over square root of 1 minus 1 over 1.52 squared minus 1 times the mass of the electron is 9.1 times 10 to the negative 31 kilograms times the speed of light, which is squared, 9 times 10 to the power 16. And they want this to be expressed in electron volts. So electron volts, that means I have to divide by 1.6 times 10 to the negative 19, and that will give me electron volts straight out, okay? So negative 31 and negative 19 is negative 12, and positive 16, that's positive 4. And the answer is going to be in EV, not in MeV, okay? Electron volts, not in joules either. So the problem then is finding all of this now. 9.1 times 9 is roughly about 81.9. So it's 81.9 divided by 1.6 times 10 to the power 4. And don't forget that factor of gamma in here, -1. Make sense? You guys understand? Yes, no, maybe?
Yes.
Okay, so all I did was assume that these electrons have to be moving at least with this speed. Okay? Because if they're moving faster, then they can produce the Cherenkov radiation. So if they're moving with this speed, then I can find the value of beta. Beta in this case is the speed, which is c/n, divided by c. So it's going to be a value that is less than 1. It should be always less than 1 beta. But gamma always should be more than 1, at least equals to 1 in classical mechanics. Okay? So in this case, we get a value of gamma. All I did now is just put in the numbers, the mass of the electrons. So these are electrons. Beta particles are electrons. So m times c squared, they can be positrons or electrons. Both of them have the same mass anyway. One of them is positive, the other one is negative. And then just juggle the numbers now, the powers and all of that. I may have made a mistake in here, so don't rely on my simplifications in here, okay? So just go through the actual formula and plug in your own numbers, and you should find the value in EV. Sounds good?
Yes.
Sounds good.
Okay. The other discussions that I think I went extensively on is problem 52, but let me talk about problems 63 and 66 because we really did not do much of them in this class, okay? But you're accountable for them anyway. So problem 63 and 66 from page 1251. So what you have in here, as a research scientist at a linear accelerator, you're studying an unstable particle. You measure its mean lifetime, delta t, as a function of the particle speed relative to your laboratory equipment. You record the speed of the particle u as a fraction of the speed of light in vacuum c. And they give you a table in there. So u over c, which is beta, 0.7, 0.8, 0.85, 0.88, 0.9, 0.92, 0.94. You cannot really reach 1, but you're getting closer and closer. You're getting warmer and more. Then they give you delta t for these different values, okay? Remember, delta t scales like gamma times the actual tau. So as the particle is moving faster and faster, you're getting now a function that looks like delta t is equal to gamma tau. So I'm discussing now problem, what is it, 63? So this is what you're plotting. Delta t equals to gamma tau, okay? But you know what gamma is? Gamma is actually equal to 1 over the square root of 1 minus beta squared. And they gave you beta. So they gave you different values for beta. And you're supposed to plot delta t now as a function of this term. So here is the deal. Obviously, if I do it, this one has this complicated form that I'm going to be dealing with. So it's not a linear function, okay? So let's study first of all. Your team leader suggests that if you plot your data as delta t squared versus 1 over 1 minus u squared over c squared to the negative 1. So in other words, calculate gamma first, squared, which is 1 minus beta squared. Since you're given beta in the table, here is the table how it looks like. They gave you beta, which is u over c, and they gave you delta t. Instead of using beta as your x-axis, use gamma squared as your x-axis. So in this case, you're given beta to be 0.7. So calculate gamma squared, which is 1 over 1 minus 0.7 squared. So you're going to get a number in here, okay, which is more than 1. Let me go quickly and share with you my calculator just to see, because I already have gamma ready for me. So the value of gamma, let me put this thing in here. Oh, I don't need that table now. Okay, so here is the thing. So beta is 0.7, so I need to find gamma squared, not gamma. So I'm going to find open parentheses, gamma of open parentheses now, 0.7. Close parentheses and close this one and square this value. Shift enter. It's 1.96. Okay. So I'm going to stop sharing. I'm going to go back into my. So this one should be 1.96. Okay. 0.78 if you really care to carry that many. Of course, delta t doesn't change. Delta t is 3.57. I'm sorry, we need to change this number to delta t squared because we're squaring the entire expression. So we're writing delta t squared is equal to gamma squared tau squared. So we need to square that number too. So we need to find somehow how much that delta t squared, which is 3.57 squared. So this should be straightforward. You don't need to have a fancy calculation. So it's 12.745. Oh no, 745. Yes. Okay. Then I do the same thing for the next value, which is 0.8. I'm given 4.41. You guys understand? You can finish the blanks in here. You can find gamma squared and you can find delta t squared.
Yes.
Okay. So you can do the rest for all of them. Then you're going to plot now. On the x-axis, you have gamma squared. On the y-axis, you have delta t squared. It should be now a straight line, which is this function. Delta t squared should be a line as a function of gamma squared, and the slope of that line should be tau squared. So it should be a line of some sort, and the slope itself should be tau squared. Okay. All I have to do is take its square root, and now I know exactly what the lifetime of this particle is. Do you guys understand? This is delta t squared, not delta t. Yes?
So the slope is equal to tau squared?
It should be yes, because look at this expression. If it's correct, okay? If I don't find the kind of a behavior that is kind of weird in this case, then in this case, hey, wait a minute. We can't really use this relationship because somehow we're wrong, okay? Somehow relativity is not correct. But if relativity is correct, delta t is basically what they did was they have different particles. They have a film in a cloud chamber, and then they see this particle moving this distance, that distance, this distance. From there, they infer the value of delta t based on the distances that are traveled or based on the distances that are traveled. And in that case, they plot in the values in here based on the speed and based on how long it lived, okay? So those are the values that they gave you. From there, you're going to assume that this relationship for the time dilation is correct. That delta t, the one that is measured by the physicist, is somehow related to the actual value tau, which you don't know, times the values that you measure for gamma based on the values of beta that you have. So what you do in this case, you find gamma squared based on beta, and you find delta t squared based on these numbers, and you plot them. If this relationship is correct, it should be a line. The slope should be this number, because that's this line. It should pass actually by the origin. It should be like this, okay? Should pass by the origin. Obviously, you don't have the origin in here because you start from gamma equals to 1 and you go to extreme values. So you start, your starting point is already gamma equals to 1. So the curve should be like this. Obviously, we don't even have gamma equals to 1. I think the lowest value is 1.96. So it's from here. Okay, but if you extend it, it should go to 0. Okay, so this is but the slope of that line should be your tau squared. Make sense?
Yes.
Yes.
Okay, very good. So now we're in business. Now the table, what is the speed of the particle relative to your lab equipment? If the lifetime you measure is 4 times its rest mass, rest frame lifetime. Okay. So we did part A. Part A, I don't know what the question was, honestly. Construct this graph and verify that the team leader's prediction. Use the best fit straight line to your data to calculate the mean lifetime of the particle. So that's the question, really, is to find tau, okay? To do the best fit and all of that, use Excel for this one. It's a good source, okay? GeoGebra also can do it. Whatever graphing software you have should be fine, okay? As long as if you can do best fit and do all of these things. So the next question was, what is the speed of the particle relative to your lab equipment expressed in U over C if the lifetime that you measure is 4 times its rest mass? Basically, if delta T is equal to 4 times tau, okay? And you know that this should be gamma tau. So this question is independent of the first one because that means gamma is equal to 4. So that, which is equal to 1 over square root of 1 minus beta squared. And they want beta. So beta should be in this case square root of 1 minus 1 over 4 squared. So that's the formula to use. 1 over, basically, you're saying beta should be equal to the square root of 1 minus 1 over gamma squared. You guys understand that this question is independent of the first question? You can always answer the second question regardless of what you find for tau.
Yep.
Yeah, okay. Then in this case, it's interesting actually to know how much that time is. So it's a good idea to find, I mean, because you're dealing with extremely short scales in this case for time, so you'd want to know if your equipment is sensitive enough to detect that take in there, okay? Because don't lose sight of the experiment. Problem 3766, which is the next one in here, deals with the Doppler shift. Okay, you are an astronomer investigating. Okay, are we done with problem 63 first, or everybody is good with it 100%?
We just need to find beta.
Yeah, for the second part, yes, beta. That's it.
Then yes.
Okay, yeah, that's all the question there is. Okay, because they don't ask you for this expressed as U over C, so that's beta. So problem 66. Okay, problem 66, you are an astronomer investigating. So you're supposed to finish all the calculation and check my numbers, okay? Because don't take my stuff as basically the absolute truth. It's not. Okay, you are an astronomer investigating for astronomical sources of infrared radiation. You have identified the nature of each source, so you know their frequencies f naught of each when it is at rest relative to you. Your detector, which is at rest relative to the Earth, measures the frequencies f of the moving source. Your results are given in this plot. So you have basically 4 galaxies, because those are the ones that we see redshift for them, which is shift in frequencies, because nearby stars, it's very hard to see that because unless they're moving super fast compared to us, okay? F, they give you F and they give you F naught. The actual frequency and the measured frequency from the vantage point. Which source is moving at the highest speed relative to your detector? I'm going to give you the formula. We did that actually in lecture, and it should be 3725, okay? We did that in lecture, if you guys remember. Square root of C plus the velocity of the source divided by C minus the speed of the source times F naught, okay? If the source is moving toward the observer, if the source is moving away from the observer, you probably have to shift the, it's not probably, you should, you have to shift the size, okay? This is because F is more than F naught. This is because F is less than F naught, okay? That's basically in a nutshell how it's going to work out. in this case, always the observer is at rest. So the Doppler shift where the observer is moving is not going to be the case in this case, the one that you did in physics 2 or physics 2, yes, and even physics 1 when you did the waves. Okay. So obviously, if you look at the frequencies in here, F, they are always less than F naught. So in this case, they are all going to be moving away from the observer. This is why it's called the redshift, because the frequency is getting less and less. The wavelength is getting longer and longer, going toward the red. So this is the formula that we really need to be using. So in other words, you are here on Earth, and these objects are moving away with the speed u. Okay, so you're going to use this formula in here because the frequency is going to be less. And you're going to find u for all of these cases with respect to c. You can use the approximation delta f over f naught equals to u over c. This is when u over c is extremely small compared to 1. Okay, this is the classical expression actually that we found also in classical physics. But this is the real expression. And now you're given different values for f and f naught. You know the value of c, and you can find the value of u if you want to. So again, which source is moving at the highest speed relative to your detector? So you can find u for u1, u2, u3, and u4. Which source is moving at the lowest speed? What is the speed? Is that source moving away or towards you? Again, all of these frequencies are less, so they should be moving away. And what frequency? You guys understand that using this formula, that's all you're doing for this problem? Yes or no?
Where do you get delta F?
Delta F is a shift, F minus F naught.
Okay.
Okay, the shift in frequency, the difference between the two. Okay. Sounds good?
Yes.
Yes.
Okay, this is an approximation. This works for the probably galaxies that are a few 100 million to probably 1 billion to 2 billion light years away from us. Galaxies that are further away, about 10 billion or 13 billion, this approximation is not going to work. You have to go back into this one, okay, because they're moving super fast. Okay, so in astronomy, you have to be careful which one to use in here, this one or that one. Okay, actually, it's not hard to use the original expression. I mean, we're dealing with square root and squaring stuff and moving things around, and that's it. Which brings me to problem 68, which is identical with the exception that there is a whole binary system. So problem 68 is similar, but here is the problem with 68, okay? You have a binary system of stars that are moving around one another, okay? One of them is moving toward the Earth at some point, and the other one is moving away from the Earth. You are here. This is where Earth is. Okay? You're supposed to look at this object, and let's assume that the entire center of mass is moving somewhere, and they give you the center of mass in here. So in this case, this star, part of the binary system, is moving toward Earth. So if this is their relative velocity or radial velocity, because they're going through a radius in here where the center of mass in here. So this is the center of mass, their common center of mass. They take them as being similar masses. This is M, this is M. The two stars have the same mass. So this is the radial velocity, okay? The velocity that you guys know, V sub r is related to omega r, where r is this radius, okay? So this is the relative velocity, and the entire center of mass is moving. Well, for me as an observer on Earth, I will note that this star is moving actually with the sum of these two stars, two velocities, I'm sorry. V sub r plus V is the center of mass, and this star now is moving away Well, the whole system is shifting in this case, so it's going to be moving with the drift velocity minus the center of mass minus the v sub r. Okay, so this is with which, so this is the speed with which it's moving. This one is the speed with which the other one is moving, and I have to use a Doppler shift. Obviously, this one is going to shift toward higher frequencies because it's going to work coming to us. So this will be blue shifted, and this one is going to be red shifted because it's receding from us. The frequency is going to be less in this case than F naught. So this is F red, and the F blue will be higher in this. So it's not going to be, it's going to be less, and it's going to be higher than the actual F naught in here. And they give you two different frequencies in here. 4.568110 times 10 to the power 14, and 4.567701 10 to the power 14. And the actual frequency, I'm sorry, they gave you the actual frequency. Hold on. They gave you F naught. Let me write it down. It's 4.568110. Okay, you have to keep so many of these sig figs because of the fact that you need to find the shift in frequency. They gave you the F blue. So the F that is shifted toward higher frequencies is going to be 4.568910. And the red shifted, the lower frequency, is 4.567710 10 to the power 14 hertz. Armed with this information, this is the star that is receding. Its shift in frequency is less than the actual frequency, and this is the one that is higher. Okay, this is the one that is coming closer to us. You should use the delta F for this one and the delta F for the second one, which is this number minus that and the other number minus that. Both of them you have to subtract the correct value and find the sum of these two velocities and the difference of the two velocities. Once you do that, then you can find the actual relative velocity or radial velocity, and then the velocity of the center of mass as the entire binary star system is moving towards us. Okay. Then using Kepler's laws or using Newton's laws that you saw in physics 1, you can find the mass m if you know the radial velocity. And they gave you omega, actually. They gave you the period with which they change. The period t is 11 days, meaning that this shift changes every 11 days. Every 11 days, they complete a full cycle. So you know t, and t, the period t, is 11 days, which you can actually use to find omega, or if you wish, this is going to be the distance. V is equal to omega r, and omega is 2 pi r. Yeah, 2 pi r over t. R is, you can find from here, since you just measured what the velocity is using the Doppler shift, using this expression in here, which is delta F over F naught, you're going to find it in terms of this velocity divided by the speed of light, and in terms of this velocity divided by the speed of light. So at some point, it's going to be the velocity of the center of mass plus v sub r divided by c for one of them, and that is for this value. And the other one, delta F, is going to be over F naught is going to be the velocity of the center minus v sub r divided by c. And these are two different values with two different equations. You can find the unknown v sub r, and you can find how fast the whole system is moving towards you. You guys agree that you have two equations in here with two unknowns?
Yep.
Delta F divided by F naught, this is F naught, and delta F, the other with delta F divided by F naught, and you will have the relative velocity or the radial velocity as they're moving around this circle. And there velocity of the center of mass, two equations with two unknowns. I need to pull v sub r from there, so I can find v sub r in here, divided by t, which is a period. They tell you it takes 11 days to go around, basically. I can find r from there, basically the radius of this distance. Okay, sounds good?
Yep.
Wait,
Once I
got a
find,
question.
yes.
Hold on. Can you scroll down just a little bit? Can you repeat the I'm sorry, the delta F1 thing again?
Delta F is just for the shifted toward high frequency. It's FB minus F naught. This number minus this number.
Okay, so it's that easy.
Yes. And delta F for the lower frequency, it's going to be this number minus the other number, or actually it's absolute value anyway. Okay. So in absolute value, it's this number still minus this number. Shifted toward the blue. Here is the actual F naught. Here is the actual FB. And here is the actual F red. So the one that is receding from us will shift this frequency to lower frequencies. The one that is moving towards us will shift the frequency toward higher frequencies. And this is what the delta F, the first one, I should call it 1, and this is 2. So this is the delta F1, and this is the delta F2, the difference between these two frequencies, okay?
Okay, got it.
Obviously, I'm using the classical, what should I call it, approximation. Really, I should use this expression for both of them, okay? I have to be careful. I use this expression to justify that this ratio is small so that I can use this expression, okay? In other words, delta F is actually this F for the first one minus F naught. So it's the whole expression minus F naught, where this U is actually not just one velocity. It's a combination of one plus the other. You have two velocities in this case, that's all. I use that to find the first one. I use the second one to find the second one. And once I do that, then I am in business, okay? I use the case for F equal greater than F naught this one, and for the case F less than F naught this one, and do the difference between the two, okay? And the difference is going to give me the relative velocity in this case, which is U, but that U is the sum of two velocities or the difference of two velocities, depending on which one I'm looking at. Then once I'm done with that, then I find what that radial velocity is. Since they gave me the period, now I can find what that R is, the distance or the diameter, the radius of that path, which is a circular path. The two stars are revolving around one another. It's a binary system. Okay, sounds good?
Sounds good.
Okay, once I find R, then I'm in business, because the next question is typically we want to find the mass of these objects. So I use Newton's law of motion that says F equals to ma. And F is just G times the product of the two masses. They're the same mass anyway, okay? And they're separated by a distance, which is twice R. 2R squared. So this is something that you learned in physics 1. Must be equal to F to ma. From the vantage point of either any one of them should work. Ma, because they're going in a circular path, is m times omega squared R, or m times v squared over R, okay? M times v squared, which is that same velocity squared over R. Cancel the R with the R squared in here, so you're gonna find G times, and the M with the M squared in here, G times M over 4R is equal to VR squared, okay? From here, you should find the mass of the star. Okay? So we know what the R is. We just computed it using this expression. We just computed also that VR using those two algebraic equations. And all we have to do now is the value of G is a constant, of course. Does this expression ring a bell to you guys? Do you remember this stuff in here?
Yes.
Yeah, this is from physics 1. What is G? The units for G are Newton squared. times meter squared divided by kilogram squared. Is this correct? Yeah, I think that's right. The units correct. Okay.
So
this is
Professor Lucidi, when we're using the time, because we're giving it as 11 days though, we'd have to convert that into seconds though, so right?
Yes, okay. Because the velocities you're going to get are in terms of meter per second from this expression. This is the ratio of a hertz over hertz, so just a number. C is a meter per second, so the velocities are in meter per second. And in order to find the R in terms of meters, which has to be in meters, then this T better be in seconds, okay? So this one better multiplied by 24 and times 3600, which brings it to seconds, okay? So you're right on that. Then once you do that, then you have the R squared. Everything is in SI now because I just plugged in the value of this one in SI. So you're going to find a mass that is a huge number, but what you got to do is divide it by the mass of the sun, because from this expression is going to be, what is it, VR squared over times 4R, and R is going to be a big number. The distance between the two stars is going to be a big number, okay? Divided by G, which is a tiny number. So this whole thing is going to be a big number. So what you do in this case to measure it in terms of the mass of the sun, so you divide by 1.99. They give you this number, by the way, divide 10 to the power, 30 kilograms. To bring this one in terms of masses of the sun. How many masses of the sun are we talking about, okay? So you have to do that conversion because I asked you to calculate it. Otherwise, the mass is going to be in kilograms, is going to be a big number. Because you have 10 to the negative 11. What you bring it up is going to be 10 to the power 11. And you have this number, which is a big number, also, which is 10 to the power 8 or 9 or 10. No, actually more, 10 to the power 11 or more, okay? And that's already 10 to the power 22. And use velocity squared, it's going to be also a big number, albeit it's smaller than the speed of light in my approximation. And here, it's going to be still a big number, okay? So, because they're only 11 days. They're very close. Remember, Mercury, which is the closest planet to the sun, is moving fast, okay? But it's already very, very far away compared to the stars. These stars turn out to be very close from one another, where their period T is very, very short. 11 days, they complete the whole cycle. So this velocity would turn out to be a huge number, okay? So this number is going to be big anyway, so when you divide it by 10 to the power 30, it's going to be a relatively small number that you can manage. Sounds good?
Yes.
And I already published and posted problem 70 for you guys, okay? Yes?
So we're doing like 6 questions for the discussion?
You're supposed to do all of the problems, basically, complete the numbers.
All right.
And
Okay.
submit them as a discussion.
I'm sorry?
And we submit this as our discussion.
This is the items of the discussion, yes.
Wait, did you say
38.
problem? Oh, go ahead.
38, 44, 51, 63, 66, 70. Okay, and what else? And 52 also. Don't forget 52. 52 is actually in one of the old videos in there. 52 is actually a good problem.
Sorry, can you repeat those numbers one more time?
Okay. We did 38 already. We did it in detail. 44. Okay. 51. 52 is in the videos in there. Okay. Then 63, 66, 68, and 70. Okay. Sounds good. Yes, everybody? Why do you say that, Natasha?
So much.
Well, actually, that's fun, man. Well, you should really enjoy these things. That's actually good. Okay.
It's a homework assignment in and of itself. Oh my goodness.
Okay. I'm hoping that you guys get something out of these things. Okay, really, honestly, because this is, I mean, because I like it, so I'm hoping that you guys at some point will enjoy these things. Anyway, here is the thing: we are at 9:30. We exceeded our basically the first period by 5 minutes already. So we're going to stop for about 10 minutes, 15 minutes, let's put it that way. And then when we come back, it's very important that we have to continue the topic. We're going to delve into something very, very, very important, and namely the Compton effect and chapter 38. So I'm going to get going with it. So do not leave. We'll see you in about 15 minutes. Sounds good?
Sounds good.
Yes, I promise it's going to be light in terms of math. So chapter 38 is not really that heavy loaded in terms of math, but it's really setting the stage for what comes next in chapter 40. Both 38 and 39 are not that crazy in terms of math, okay? So I'm gonna pause the recording, and I'll see you in 15 minutes. Please don't leave, okay? Hi guys, and welcome to the second part. You guys are back?
Yes.
Yes.
Okay.
Yep.
So let me introduce chapter 38 to you guys. Hopefully we'll make it a little bit light, okay? And tell you exactly what problems we were running into at that time. So imagine with me this experiment. So actually we need to add a new page in here. Let's call this 138. Okay. So basically, let me describe the experiment first that we were running into. So in a sealed container, usually like a glass, or what do you call it, a spherical object, the pressure is lower, so you need to really remove as much as pressure as possible. Okay, remove as much gas as possible in here. And you have usually a cathode that is connected to somehow to a battery. So you have a battery in here, okay? This is the positive, that's why this is a cathode, because it's connected to the negative side. And you have the anode in here, and there is a gap between them, okay? So this one is connected to a galvanometer. First of all, the reason why you need a galvanometer in here is so that you can detect the tiniest currents there is. Okay, you don't need just an ammeter, you need a galvanometer. Okay, you did a galvanometer in physics too, didn't you guys? Do you guys remember that idea? Yes.
It doesn't sound familiar.
Yeah. Same here.
I think who said that? Was it Natasha who said that after the finals everything is forgotten? That's good, actually. She put it correctly. Is that her or somebody else?
No, that was her.
Yeah, that was her.
Anyway, so she was right on that. Okay, is she still here?
She's here.
Okay, good.
Yeah, I'm here, sorry.
Okay, and here we have a rheostat. You know, guys, you did the rheostat also in physics too. That's a device where you can vary its resistance. So R in here is variable. You guys remember this symbol from your physics 2 class, the rheostat?
Yes.
I don't know if I'm writing it correctly, but I think that's how you write the rheostat. Anyway, the point being in here is you have a voltage, you have a battery. If you run the current in here, and if nothing is happening, all you're going to see is that you're going to see a current. Let me draw the current with a different color. So you're going to see a current running this way, meaning that the electrons are actually traveling from the negative side, coming through the rheostat in this case, and they come in here because this resistance is infinite. There's no problem with that, okay? So what happened now, this is what happened when you shine a monochromatic light on this, a monochromatic beam on this. All of a sudden, this galvanometer starts to register readings for certain frequencies. So this is a monochromatic beam. monochromatic beam of light. Okay, you start to see readings on the galvanometer. That means current is actually being split in here in part, electrons are split in part in here. Part of them are going in here, and they are actually traveling this gap in here. This is vacuum for all practical purposes. So they jump from the cathode to the anode in this space in here. So we have electrons that are traveling this distance and they're collected in here. Well, in this case, since I have a current that is flowing, I can measure it with the galvanometer. I have a voltage in this case. It's usually called VAC, okay, where the points A and C are between the anode and the cathode, okay? So there is a voltage in here between the anode and the cathode that somehow created this current. Where did I leave my glasses? I think I left them in the living room or somewhere else. Anyway, the point being in here is there is a voltage. I can tinker around with the voltage by changing the rheostat in here, and it can have higher or lower voltage. So what we knew from Maxwell's equations is light is a wave. And a wave has energy. So this monochromatic beam is energy. Basically, I'm hitting this cathode and somehow I am extracting electrons from it. And these electrons are moving in vacuum. And this voltage now is somehow causing them to move in such a way that they reach this point and then they complete the circuit, okay? And they come back to the positive side of the battery. So this is basically the observation. So if somehow I increase the intensity of this beam, I should see more of these electrons to come through. But there is a problem. There is a big problem in here. The energy in here of this monochromatic beam has to do with the intensity of the light, and that's it. Shine a very, very bright light on the material, and you should be able to extract more electrons, if that's the case. But that's not what is observed. What is observed, first of all, there is a cutoff frequency below which the galvanometer reads no current. There is no current going through that at all. So you need a minimum of frequency so that you can see this phenomenon. You can see that reading. Below that, there is no reading, okay? As a matter of fact, what I can do is I can reverse the polarity of this battery. I can keep on changing or reverse the polarity of this battery so that the battery is pointing in the opposite direction. If I have a bright enough light in here, this should cause the electrons that are moving around to turn back and basically not complete the circuit. So at that some point, this reversal of the current will stop. This reversal of the battery will cause the current to drop to zero. So this voltage in here is dropped to the point that it reaches a V naught, and this V naught is called the stoppage voltage or the stopping voltage. The voltage that causes I to drop to zero, okay? Even if I have a frequency that is greater than this cutoff frequency, we didn't understand where this was coming from. First of all, here is another problem. Let's say, for example, I shine it with a monochromatic beam that has that cutoff frequency or more. So now I have currents, but I drop the intensity a lot. So I make this intensity as small as possible. So it's going to be a low intensity, high frequency beam, basically. Okay, what happened? I expect the following. The energy is not enough because it's low intensity. It doesn't have intense beam anyway. So I expect that the electrons, the first beam that hit it gives it a little bit of energy. The second one, a little bit. The third one is a little more and more until enough energy is there so that it frees it from the material. Because every material, which is tungsten most of the time in this case, has a work function. This is known. What I mean by work function is the energy needed to remove one electron. I mean, it's not cheap, I mean, to remove one electron. That's what I mean by the work function. Phi, the symbol for it is phi. So we know that there is energy needed to extract electrons from material. And this is exactly what this intensity is supposed to do. It's supposed to give me enough energy to extract this electron. But if I do a low beam, there is not enough energy, low intensity beam, there should not be, even with high frequency, there is not enough energy in it. But if I wait and wait and wait, that energy starts to pile up, build up, build up, build up, because I continuously have a low beam, a low intensity beam hitting the material. So at some point, that energy builds up, and then the electron should be freed. So there is a delay. I'm expecting a delay. Here is the kicker, though. This is not observed. So something is weird is going on in here, okay? First of all, where is that cutoff frequency is coming from? Why? I think this should work for all frequencies, especially high intensity beams, because they have a lot of energy, even for low frequency, okay? Because they carry with them, if it's a wave, they carry energy, and that energy is proportional to the square of the electric field, actually, if you guys remember from chapter 32, okay? E squared. If you guys remember, I don't know if you remember that or not, the energy density for the electric field, or that of the magnetic field actually, is 1/2 of, what is it, epsilon naught times E squared, where E squared is the maximum electric field. And for that of the magnetic field, which is also part of the electromagnetic wave, it's 1/2 of B max squared over mu naught, okay? This is the energy density. This means that it's energy joules per cubic meter, okay? And this is joules per cubic meter. You do the calculations based on that, and you find the total energy on a given volume. You guys remember these expressions from your physics too?
Yes.
A little bit, yeah.
Yeah, so it's proportional to the square of the electric field, which is the intensity. So the more
Are those user
intense.
X's?
Sorry?
Are those user X's?
Use. The energy density, usually they use lowercase u, which is big U over volume, okay? Which is actually du over dv. Energy density, it's in joules per cubic meter, okay? So anyway, this is the electromagnetic energy, one of them for the electric field and one of them is for the magnetic field, but both of them are proportional to the intensity of the field squared in this case. So the higher, the brighter the light, the more energy you should get out of it, okay? So that's the bottom line. But I'm not getting that. If the frequency is not above the cutoff frequency, no matter how bright the light is, this galvanometer is going to read nothing. It's going to give you nothing, okay? And if it's above the frequency now, I do the opposite. I make it very, very low intensity beam. It's still higher than the cutoff frequency. Usually that cutoff frequency is in the UV range, so which is really high energy, okay? Cutoff frequency are in the UV. Okay, for most materials, there are some materials that are actually in the blue light. I mean, not the blue, the yellow light, which is actually a low beam, low frequency, and sometimes probably blue. But most of the times, I would say the vast majority of it. I think what is it? The material that I think it has. Oh, I forgot. I think tungsten with some sort of an alloy that has a yellow light. But most of them, they're actually in the UV radiation, which is really high frequency for those days. We're talking about the late 1800s, okay? At that time, X-rays were not discovered, which is even higher than the UV. So this stuff is a problem for us, because even if I bring the UV light, okay, and shine it on that material, and make it low beam, I expect a delay, because there is not enough energy in it when it's low intensity. There's not enough Emax or Bmax to give me that right away response so that it frees the electron immediately, because you need a lot of energy to get one electron out, which is the work function. Yet what happened is, the minute I shine a frequency bigger than the cutoff frequency, this reading starts to come out immediately. There is no noticeable delay. The lab could not produce that delay. That's a problem. So we needed to understand where there is something else is going on. Here is where Mr. Einstein came in. He noted a few years before that Mr. Planck, to explain the black body radiation, which we're going to come back to it, by the way, which is really part of physics, which is part of the first 4 chapters. You take a material, you heat it up, it's going to radiate energy, and you measure the frequencies, and as the frequencies are measured in the black body radiation, we're going to come back to this one, by the way, it's going to have this pattern. This is lambda, this is the intensity, it has this pattern here. It's max at some point in here at lambda max, it has a maximum distribution, but then this is how, depending on the temperature, of course, different temperature, higher temperature will have a higher, and is actually, there is a shift. I'm not drawing the shift in here. The problem with this black body radiation is the following. For long wavelengths, that means low energy beams, there is no problem. There is a match with the theory and the experiment. But for the high frequency, short wavelength, namely the UV, there is a mismatch between the theory and the experiment. This is how the theory says the pattern would look like. There is no actually, it's going to grow. And this one also grows. This is for a T higher, and this is for T low. So that's basically 2 different temperatures, 2 different, you know what I'm talking about. Take a material, piece of iron, put it on the stove and wait for it. It starts to glow. If you wait long enough, it builds up heat and it starts to glow. And if you wait longer, the color changes from dark red to yellow to white. White means that all the colors now are in, okay? And if you wait for it long enough, that hopefully it doesn't melt. that's basically what we're talking about, okay? And measure the frequencies. This is the experimental data is the black one, and the theory is that. There was a problem in here called the UV catastrophe, ultraviolet catastrophe. People didn't understand it. So Mr. Planck came in and says, wait a minute, if the energy of this stuff is proportional to the frequency, if the energy of the radiation is proportional to the frequency, he used something that he didn't like, which is Maxwell Boltzmann distributions, and he came up with a perfect fit for the data from the experiment, provided that this assumption is true. He spent most of his life, at least the first few years of his life, not knowing where that term came from, but that worked, and he was puzzled with it. Being a theoretical physicist, that was a nightmare, because he had no justification for this expression. Where h was just a constant. Later on, h was found to be 6.626 times 10 to the negative 34 joules second, okay? That's the unit for it. Because the frequency is 1/2 times second from this expression, and the energy has to be in joules. So this number, this expression made no sense to him, but it worked. It made him famous, albeit he was kind of shy about it. Einstein was not shy about it. He took that same expression and he used it for this phenomenon. And he said, what if this light in here that is hitting this cathode is actually also has the same energy, E equals to HF. If E is greater than the work function, then I can free up my electrons. It doesn't matter how high the how much intensity you have, as long as the frequency is greater than the cutoff frequency, which is just the work function divided by H, then you're going to have electrons floating around. And you're going to see the galvanometer making the reading, because these electrons, they can make it with enough voltage, they can make it in here, and they complete the circuit. Because an electron, in order to make it to this point in here, it has to have at least a kinetic energy, which is given by the conservation of energy, 1/2 of mv squared equals to EV, where that V is that AC, the voltage between the cathode and the anode. So in this case, so this is the minimum voltage to break it all the way to the anode. So as long as they have this speed, they can make it there, okay? So he's saying in order to bring those charges in here, all you need is just this energy, and that is your cutoff frequency. From here, you can find the cutoff frequency. So basically, as long as the work function is equal to that H that Mr. Planck has introduced, later on was called after him, Planck's constant, times the frequency. That is the minimum frequency. So this is your cutoff. This is the minimum frequency. Higher than that, you're going to have no problem. Lower than that, you don't have enough energy to free up the electron. So this is the F cutoff, if you wish, must be at least equal to phi over H, the work function over H. So that was an explanation for this. Furthermore, he said that in order to, when you reverse the polarity of this and you cancel the current, so what you're dealing really with is using the conservation of energy. Anything higher than this cutoff frequency, anything higher than the cutoff frequency will give you enough energy, hopefully, to make it to the other side in such a way that EV is equal to, what is the expression? HF, this is the excess energy over that phi, okay? And from here, you have an expression that that is another thing also. This voltage, part of the experiment, was shown to increase with the frequency in a linear fashion. That was also the experiment too. So the experiment yielded no delay. The experiment yielded the cutoff frequency, and the experiment also yielded the proportionality of this voltage with the frequency. All of them have completely no bearing whatsoever on Maxwell's equation. I mean, you cannot find them in Maxwell's equations. You cannot find them in the wave nature of light. So we're faced now with a dilemma. Mr. Einstein proposed that these things are quantities of energy that the photons, as they hit the material, he didn't call them photons, he called them the quanta of light. As the quanta of light, they hit the material with enough energy, which is HF, they free up an electron, each and every one of them will. Call them the quanta of energy, the quanta of light, and later on that name was changed to photons, particles of light. So now here is the idea. And there is no delay, because as long as they have that energy, they immediately free up. It doesn't matter how much intensity you have. So all of this theory was explained using this phenomenon. This is known as the photoelectric effect. And this explains the photocurrent and how it is formed. Okay, so this is what really made Mr. Einstein famous. And this is how Mr. Einstein won his Nobel Prize, not the work that he did in relativity. Okay, so now we have a perfect example. We can draw this line, which is just a curve. Furthermore, the stoppage current turned out to be a function. So this is the voltage. This is the current now. The current, of course, is going to stay the same for the same intensity If you double the intensity, the current will double, and that's it, as long as the voltage. But if you put it in the opposite direction, it's going to drop to a certain point, and at that point, this is the stoppage current. The stoppage current does not depend on the intensity. It's always the same for the same material, okay? So all of this was basically the ideas behind the experiment. And this is the photoelectric effect. And this is part of the next lab that we're going to be talking about. Sounds good, everybody?
Yes.
Okay. Right around that time, in 1895, Mr. Röntgen, you know how the Röntgen, the T comes before the G. Okay, did another kind of experiment, and he found different kinds of results. Let me explain what that is. He did the process basically backward. Okay, he did also in a vacuum. This pressure was almost, I think, 0.01 or less, 10 to the negative 7 Pascal, which is extremely small. I think this pressure was like of the order of 10 to the negative 2 Pascal. So this was low pressure, but this one is even lower. This is the pressure on Mars, by the way. This is even less than that, okay? So the pressure was very low in here. And you have a filament again that is connected to a battery. So this is a heating, an element usually of tungsten that is heated with the Joule heating that you did in physics 2 also, namely the energy in this case is going to, the power actually, is going to be Ri squared, okay? Where I is that current that is flowing through this resistor. So if I wait a long time, there will be enough heat generated in this one, so that becomes this one super hot. You guys remember this stuff from your physics 2? The Joule heating? Yes, no?
I don't remember much from physics 2.
Are you serious? This is fundamental. This is from Ohm's law. Ri times I. This is the power. This is the voltage, and this is the power. No, this is the current. So the whole product of VI is equal to the power. This is important. This stuff is, this is Ohm's law. And this is the power. The power is voltage times, wow. Okay, you cannot go in life, I mean, without knowing these two things. This is the Joule heating, okay? It's extremely important from physics 2. Actually, should be heavily tested on it. Okay, so enough talk about that. You know, anyway, so this is now so hot.
Professor, what does P represent?
P is the power. This is physics 2. Okay, it's important, okay? It's very, very important. I think around chapter 25 maybe, or 26 at most. Okay. This is probably far more important than the stuff that we're discussing right now. For most of you who are going into engineering or life sciences or anything else other than physics. I mean, even in physics, this stuff is important, okay? So this is worth remembering. And it's if this is F equals to MA, this should be here, okay? Next to it. Anyway, I'm going to connect this one now to another battery, and I will explain what I'm doing in here because of the fact that this will be so hot that at some point the energy in here that is produced, because if you wait, remember the energy is just the integral of the power over time. Remember, power is the rate at which work is done or the energy is dissipated in this case. So the energy in this case is just the integral of p dt. So it doesn't matter how long I wait, I will have enough energy in there that is built up. That is actually what the Joule heating is. So in this case, what's going on in here, there is enough energy in it to overcome the work function. In other words, there are free electrons in here floating next to this material when it's so hot. Okay, they're ready to go. Sounds good? Because there is U is bigger than phi. So now I have enough heat to ionize this material. Basically, this is the thermoionization process. So this process is thermoionization. Okay, that means with heating it enough, you will have enough electrons floating. Now, here's the deal, though. I'm going to take this and connect it to another battery now with another voltage, and now I have another material in here, a slab of material in here waiting. Okay, so this is going to be a positive, this is going to be a negative. So what this does in here, it creates a potential where this charges are going to move now. So there is a difference of potential now. Usually it's a very high potential. Okay, I'm going to call it, what is it? Let's call it V naught in here, okay? V naught that is very high, that is going to cause this electrons now to accelerate and hit this material at extreme high velocity. That velocity will be very, very, extremely high, to the point that these electrons now, when they hit the material, they have to slow down to a standstill. So they have to break into the material. So this is the slab of material. Usually it's tungsten, okay? If you go to the hospital and they do X-ray on you, that's what they use, okay, to produce it most of the times, okay? It's tungsten. Anyway, tungsten, by the way, the symbol for it is W. I was kind of surprised. I was looking for it today in the periodic table. And this is one of the elements I don't deal with on a regular basis. So I don't know. It's W. 74, okay? Anyway, the material, once it hits it, it has to slow down in it. And from chapter 32, I think, for the radiation, when a charged particle is accelerated, in this case is decelerated, it's going to emit the radiation that is proportional to the acceleration squared. In this case, it's a deceleration, okay? So the light that is going to be emitted is proportional to this, how much they are going to be slowed down in the matter. Remember, they are accelerated already with an incredible speed in here because of this potential. Each and every one of them has an E times V naught. In the classical approximation, it's going to be, they have the kinetic energy 1/2 of mv squared, and they come to a standstill. So their final energy is 0. Their initial energy is 1/2 of mv squared. When they slow down, before they slow down, actually they gain that kinetic energy through the process where each and every one of them is got this much kinetic energy. Obviously, in the quantum mechanics, in the relativistic approach, we have to use this expression. Each one of these electrons is given by this V naught here. That's just fresh from chapter 37, and it's true if gamma is very close from 1, that this reduces to 1/2 of mv squared, where this is the velocity and this is the potential that accelerated them. Once they stop, though, you can compute how much acceleration you're going to have by taking that kinetic energy and bringing it down to 0. And that will be enough for you to see that there is a deceleration and you're going to produce extremely high frequency radiation. They have a name for this kind of radiation. In German, that's the first experiment where they were using it. They call it the Bremsstrahlung, which is really stands for braking or brake radiation. You know, when you hit the brakes on your car? That's what I mean by that, because you take electrons that are moving super fast and they slow down to a standstill, okay? And they radiate energy. That energy now has extreme high frequencies that are extremely high. I mean, look at it this way. UV radiation remember, the red light is around 700 nanometers. The blue light is about what, 450, maybe 400 nanometers, 450, around 400 nanometers. The UV, you're talking about a few hundred nanometers, usually between 200, I mean, below than that is UV actually, all the way to probably some 100, maybe 70 nanometers or so, okay? So this is the UV radiation. We're talking about now orders of magnitude of a nanometer. This radiation is 1 nanometer all the way to 1 picometer, which means from 10 to the negative 9 meters all the way to 10 to the negative 12 meters. This is extremely high frequency, extremely short wavelength that we never dealt with. The energies associated with this kind of energies are incredibly high. Okay? Unbelievably high. They will do a lot of damage. So these things are never heard of. So in 1895, as I was saying, Mr. Röntgen, who was a German physicist, was his first name, I think, Wilhelm, I think. Okay, I don't remember exactly. Anyway, he was able to produce them, and this is the Bremsstrahl break radiation, Bremsstrahling, which stands for break radiation. Here is the problem, though. I mean, expect to have all the frequencies also there. Because if these particles, if these electrons are really slowing down in the material, I should see frequencies also lower. Because some of them will probably, here is what I'm saying in here. Here is what I'm talking about. This is the atom. This is the nucleus. And these are the electrons. Some of these electrons, they come in basically hardly affected by the electrons. Those, they should continue for the most part, slowing down little by little. Those, they should produce low frequency beams because they are hardly, they will be changed. Others, they will be completely, how should I say it, bent. And this will cause a deceleration because of the fact that they slow down. And the next one is going to be slowed down. So this would be higher frequency than this one. Yes, I can understand this part, but I have a problem with this ones. I should see also the low frequencies. I don't see them. Furthermore, there is, let me explain what the results of the lab is first, okay? Depending on that V naught, depending on that potential that created them, this is lambda, by the way, and this is their intensity. This is how the curve would look like. No, I'm sorry, it doesn't drop to 0. It goes to it approaches 0. Let me take another voltage, okay?
I is current or intensity?
I'm sorry, this is the
What is
current, the intensity of the beam that is produced, because the radiation is produced now. Remember, as these things are slowed down, this is rays that are produced from this one. So this is light that is coming out. At extreme high frequencies, I can see the light. I cannot, but I use a different process that you guys have seen in chapter 36 called the Bragg, what is it? Scattering, where I can find the frequency that is actually emitted. Chapter 36.6 or something like that. It's basically as this radiation goes through the material like NaCl, for example, it's the spacing between the sodium and the chloride, in this case, causes the wave to be shifted, and there is an interference that form after that. Based on the interference, I can find the wavelength of these quantities. So these quantities can be measured with extreme accuracy, although you don't see it with your eyes because these are extremely high frequencies, but you can measure their wavelength. And the wavelength that you measure and the intensity based on the wavelength is drawn in here, okay? So this is the wavelengths that are drawn for the approaches 0, but it never goes to 0. Anyway, these are low wavelengths, but there is this problem in here, the cutoff frequency. So there is a lambda naught in here. There is a lambda naught in here that is cut off. That is a problem. How in the world we're going to get? Why are we not getting this higher energies than this? We always seem to get we hit a wall in here. okay, for the wavelength. I'm sorry, this one is produced. It's really, there is another phenomenon. I will tell you what that is. It seems like some of these electrons come in and they stop completely at their tracks. They're absorbed completely, okay? And this is what produces those cutoff frequencies. Let me just point out that there is a problem with the data, actually, the way that I'm doing it. There is actually few lines that seems to be coming out in here. Depending on the material, they're always the same lines for the same material. But of course, this is for different voltages. Different material will produce different lines. These are called the characteristic radiation. In this, the continuous one is actually the Bremsstrahlung radiation, okay? If you're going to be in the medical field, you need to be familiar with these things because they explain this in detail, and they go more in detail because they deal with X-rays a lot, especially in a lab that makes these things, okay? And they expose people to them. Okay, anyway.
Are those the lines that we see, I can't remember, from chemistry, like we saw like different colored lines? Yes.
Kind of, but this is special for this event, okay? Because yeah, spectral lines that have to do specifically with them. And you're absolutely right on that, because we're going to get into it at some point. Those lines, they involve the lower energy shell, which is called the K shell. And those actually, they get knocked off by these electrons. So the electron now is get out, and the higher energy electrons, the ones that, not higher energy, I should say, the ones in the higher levels, they jump in here to replace those electrons that are knocked out, and they emit actually this characteristic lines. So characteristic because they're specific to the material, okay? And they're spectral lines and special kinds of spectral lines, because most of the spectroscopy that you do in chemistry, or all of chemistry, deals only with the outer shell electron. That's it. All of the new chemical reactions and interactions and everything else deal with this one. They're low energy events anyway, chemistry and processes, and they are actually the spectral lines that you're dealing with. They deal with these transitions, okay? But what we're doing in here, we're causing actually inside, well inside the shells of the electrons to get them out of there. And in doing so, this electrons will move all the way down in here, making those spectral lines. Obviously, depending on where we're transiting from. If we're transiting from this level or from that level, I'm going to get this characteristic or that characteristic, but all of them involve that the low energy, I mean, not the low, the closer ones, they're extremely high energy, extremely bound to the nucleus, actually. They require a lot of energy. And it seems like these electrons, the ones that hit it, had enough energy to knock it out of the shell. Now the K shell is empty, it has to be filled immediately. And that's what I see in the spectral lines in here. Those are called the characteristic radiations. But what interests me right now is a continuous spectrum, because it has a cutoff in here. Make sense?
Yes.
Okay, here is the deal with this thing in here now. Even with the characteristic radiation, the only way to explain this one is HF. It seems like light is made up of this quanta of energy that at some point, first of all, these characteristic lines have to do with the HF. The only way, and we're going to come back to this one, by the way. The book does not draw this picture in here because it's an incomplete picture, because we're going to come back to it. We're going to come back to the K shell, the L shell, but the K shell is the one that is involved, this one, this transitions, okay? But the other part, which is the break radiation or the breaking radiation, whichever you call it, why there is a cutoff in here is because some of these electrons, they get absorbed completely and they lose their entire energy that they already have acquired, which is that gamma minus, which is EV naught, that's accelerated them anyway. From here, I'm going to find this is equal to H times F. And remember, F is related to the dispersion law. The speed of light is the frequency times the wavelength. From here, I can find F being equal to C over lambda. So this is S H times C over lambda. And from here, I'm going to find the value of that lambda. Lambda seems to be inversely proportional with the voltage. Okay, with the voltage. Depending on how much voltage I have, if the particle gets completely out, this is the one that completely stops it. This is the lowest value of the voltage, the value that I'm going to get, which is the lambda min. After that, the particle actually can get deviated and they can move on. So you don't need this, okay? So for those particles, you can use the other expression, which is kind of complicated, honestly. I think there is an E squared in here divided by C to the power 4, and there's some term in here, which I forgot the whole thing, and this gives me the radiation that is produced. Anyway, you can find the deflection, and you can find the minimum distance approach, and you can find that value. So that value can be easily explained in here, but this one really is related to the V that created those particles. I call it V naught in here, okay? So that explains that phenomenon beautifully. And the other one, the characteristic radiation, if anything, it reinforces this nature of light. So I can come in here and explain the photoelectric effect using H equal to HF, and I come in here and also explain what's going on with this one using E equal to the same thing, HF. Here is the problem. Remember, in relativity, for any particle, it has this energy. Light, on the other hand, does not have mass. These particles, which are called photons, from this point on, we're going to call them photons, they have no mass, they have no rest mass. So in this case, the energy must be equal to PC, because this is 0 square root of P squared C squared is equal to PC. That means it has momentum, and that momentum is simply equal to E, which is HF over C. So this is the momentum of these particles. So we have particles now of light. So light is a particle. It's no longer a wave, but now we're moving to the fact that it's a particle. Because it's a particle, it has energy, yes, and the energy is equal to HF, but we need a momentum for it, and the momentum for it is this one. So this is the momentum. Somebody asked me earlier about that P, and you're absolutely right. That was power. This is momentum. So in physics, we usually use P for power. We use P for momentum, and we use P for pressure. Hopefully you guys are not confused about the P's, because I used the P today probably 3 times already. The pressure inside those chambers, the power and the Joule heating, and now we're using P for the momentum. Any objections about these P's? No?
Nope.
Okay, so sorry about that. Okay, that's basically part of the nature of the beast, nature of the thing. Okay, so anyway, so light now is a particle. It has a definite momentum, it has definite energy. But when I say a particle, I'm using it loosely a little bit in a sense, because you're asking, it doesn't have mass. Well, it has momentum, because if all you care about is the momentum, which is mass times velocity in the old classical physics, well, in this case, we also have momentum, and here it is, given by the relativistic value from this expression. By the way, you use that same expression when you did the solar sailing in physics too. We use the same expression here, basically, when you build sails. Now the Japanese, they have the project going on where they use sailor sailing to go in between the stars. Anyway, so the point being in here, we use this expression also. We use that same expression for the energy and the momentum, because you need momentum there too, that is imparted by the radiation, the solar radiation as it hits the sail, and that momentum is transferred to the sail, and the sail moves forward. Okay, so anyway, the point being in here is that we are dealing with a particle now. Okay, the next has a little bit of math, and it's up to you guys. How do you feel about it? Should we get into the Compton effect, yes or no? Or we leave it until Tuesday? We can get into it now, and hopefully we advance a little bit in the topic.
Leave it till Tuesday?
Yeah, I think it was a lot of
Yeah,
info
leave it till
today, to be honest.
We have
I
8
should-
problems to do.
I should not ask it, okay? Okay, I should not have asked. They should have probably moved on and assumed that, no, okay, never mind. Anyway, the point being here, here's the deal. Mr. Compton in WashU, Washington University, I mean, if you live in live there in St. Louis, that's how they call it in that area, in Del Mar area. He was in 1923. He was experimenting with the with this high energy frequency lights that we're talking about now. Okay, and he came up with a phenomenon that it was puzzling, but he immediately recovered because he knows about what Mr. Einstein has done. He knows about basically the work that led to it. For that, he took that idea, and he took the relativity also, and he came up with an explanation for it. That is the heaviest math that we're going to see in this chapter, probably. Okay, and that is the Compton scattering. After that, we're going to have the Heisenberg uncertainty for this kind of phenomenon. So here is the deal from chapter up to 38 up to this point. Light is not a wave, because if it is, we cannot explain the photoelectric effect. We cannot explain that cutoff frequency, that frequency for the breaking radiation, if you wish, and we cannot also explain the Compton effect that is coming soon. Okay, so light is not a wave, but you're saying, wait a minute, light is a wave, because Mr. Young experiment also in 1800, in the early 1800s, that you can do now, and you did actually in the lab for the double slit experiment and the single slit experiment, shows that light scatters like a wave. You have the wave patterns, you have the dark fringes, the light fringes, and all of them formed. And you did the experiment, works beautifully. So then we must conclude the following, that light is sometimes behaves like a wave, sometimes behave like a particle. So it has a dual thing. Light is kind of a, how should I say, has a split personality, suffers from schizophrenia, okay? But that's not really the thing, okay? I'm just using them probably in here. But the point being in here, light behaves as a wave and a particle. That's the conclusion that is going to come out of chapter 38. Chapter 38 and 9 will take the problem backward. We'll go to the electron, and particles now start to behaving, not just like particles, but they also have a wave nature. So the duality wave particle starts to exhibit itself both for waves and then for particles. And it turns out that everything has this wave nature in it, in addition to the particle nature, depending on what kind of experiment you're doing. You guys understand where we're going with the big scheme of things?
Yes.
Yep.
Chapter 40, though, will take that duality and start treating particles as waves and come up with a wave equation, which is the Schrodinger's equation. And then chapter 41 extends on that one for the three-dimensional, the real problems, really, because chapter 40 does it only in 1D. Hopefully you guys are seeing the entire course now being laid out in front of you. Sounds good? Yes? Maybe?
Good.
Yes.
Sounds good.
Okay, so I'm gonna stop the recording, and I will see you guys on Tuesday, same time. Okay.
Thank you.
Bye.